Okay, Assalamualaikum and good morning. Today we're going to talk about regression analysis, which is a statistical method with widespread application in solving chemical problems. We obtain data from experiments, and then sometimes we have to plot a straight line curve to do either for calibration purposes. For calibration, sorry, I didn't know it's yours. For calibration, for extrapolation, for finding gradient from the straight line, or for prediction of parameters. This is one example where we have to use the straight line relationship between two parameters from experiment. And this is usually called calibration in analytical chemistry. As an example, we measure the concentration of series of standards in UV spectrometry, for example, or in IR spectrometry, or even in chromatography, where we plot the peak area against concentration. So in this case, we have a series of concentration for standard compound, and we measure the absorbance, and we get the straight line relationship using Beer's law, relating absorbance to concentration. Where is the intercept, C? The intercept C is here, where the value of concentration is 0, and this is the gradient M in the equation. This is frequently used in analytical chemistry, especially when involved instrumental method, and we use the curve to estimate the concentration of unknown sample. So we just plug in the value of absorbance for the unknown sample, and then we get its concentration based on the calibration curve. We can also use the straight line relationship between two variables for extrapolation purposes. In this particular case, we measure the parameters at certain condition, let's say around room temperature, and then plot a straight line using the value that we obtain at that particular temperature, and then we extrapolate to temperature 0, for example. And in this case, we can't make the experiment at very low temperature. Therefore, we use the extrapolation to get the value at temperature 0. So this is called extrapolation. And the same straight line is drawn based on the experimental data. In the third example, we use straight line relationship between two variables to find the rate constant. And in this particular case, we have first order reaction involving compound A, and we plot concentration of compound A against time. We have to use log to get a straight line. Log concentration of A against time will produce a straight line curve like this. And the gradient of this curve is minus K, where K is the gradient. Sorry, the rate constant. The rate constant for that particular reaction. So we are not interested in using this for prediction or for extrapolation. We are only interested in the K value, which can be obtained from the gradient. Of course, the K value later on can be used for prediction of how fast a reaction can proceed. And the last example, we can use a straight line relationship to predict the certain parameters which cannot be otherwise be predicted or be observed using the usual condition. Let's say we have a compound and we want to determine number of the identity of that compound using chromatographic method. We can plot number of carbon in that series of compound. Let's say we have standards involving alkane, yeah? C3, C4, C5, C6, 7, 8, 9, and so on. And we plot the retention time of this alkane, against number of carbon in the structure. And we can get a straight line relationship like this, provided that we use log retention time. And then we can use this plot to predict what is the number of carbon in the unknown compound. Using this plot? We run the separation using the same chromatographic condition and get the TR value and plug in the value here, and we can predict what is the number of compound in that particular, what is the number of carbon in that particular compound. So this is the use of straight line curve to predict parameters which otherwise cannot be obtained experimentally. So these are some of the application of straight line relationship used in chemistry, and we can look at further into the detail of how the line is derived. And then in all these conditions, usually we save the line in the form of equation. For example, in the first one, the equation that we must save is y equal to mx plus c. The two parameters that we need to save the equation is just the m and the c value that we obtain from the standard solutions. Once we have saved the two values, we can use the two values to predict concentration of sample in the concentration of analyte in the unknown samples. So the key point here is to derive this equation, to obtain this equation. Let's go into more detail on the equation. In statistics, the equation is called simple linear regression equation. Y equal to mx plus c is a very simple form of simple linear regression equation. The term simple here means that there is only one variable. Simple means there's only one variable, in this case x, x1. There's only one variable. Linear means there's no quadratic term in the equation. There's no x squared or x cubed. So just linear equation. So simple linear regression equation is a general term used to express the equation that we use for calibration, for prediction, for extrapolation, and so on. So this is the term that they use in statistics to generalize the equation developed from the experimental data. The equation is yi equal to beta 0 plus beta 1 xi plus some error. And mind you, this is the true equation relating x and y. The true equation based on the population. What is beta 0? Beta 0 is the intercept in this curve. It's the intercept when x equal to 0, we have value of y which is beta 0. So by definition, beta 0 is the value of y when x is equal to 0. What is beta 1? The gradient. The gradient is, if you can see from this plot here, is an increase in y when we increase x by 1 unit value. Let's say x is time. When we increase x by 1 second, how much y will increase? If x is concentration, if we increase x by by 1 ppm, how much absorbent will increase? Or how much peak area will increase? Follow me? Okay. It's too early to get lost in the morning. Okay. So beta 1 is the gradient, which is a measure of how much increase in y when we increase x by 1 unit. When we increase temperature by 1 degree centigrade, how much increase in y? When we increase x by 1 ppm, how much increase in the absorbent? Y is called the dependent variable. Y here is called dependent variable because its value will be determined by value of x. If x increases, y will also increase. If the direction of the curve is this way. If the direction of the curve is the other way, y will increase when y will decrease when x decreases. When x increases. Sorry. X is independent variable because its value is not determined by other parameters. It's independent variable because its value is not determined by other parameters. Unlike y, which is very much dependent on x. There's another term used for y and x, where y is called y is called the response variable, and x is called the predictor variable. Y is the response, and x is the predictor. Why this is called this way? Because we can use x to predict value of y. We can use x to predict value of y because when we increase the concentration, the absorbent will increase. So more or less, we can predict the absorbent based on the value of y. When we increase the concentration of the metal, and the concentration of the metal become a predictor variable. So another term used besides the dependent and independent variable is response and predictor variable. Y as the response and x as the predictor. We predict value of y based on x. Y is the response when we manipulate the value of x. There's a change in y when we change x. Okay. As I mentioned just now, this equation is for the true relationship between y and x. And in order to get this, we have to get the whole population of the two parameters, which is not possible. So we estimate the value of y and x. We estimate, the equation relating y and x based on our sample. Based on sample. Example of sample. The standard solution that we use to develop the curve, right? When we develop the curve, what we do is we make series of standard solution with concentration of 10, 20, 30, 40, and 50 ppm. And then we measure the absorbance of the standard sample. We measure the absorbance of the standard sample. So this solution are samples of the population, sample of the true population. It's impossible for us to measure all concentration. So we take some sample of the solution with concentration 10, 20, 30, 40, 50, 60, 70, up to 100 ppm. And we plot a straight line curve relating the concentration and absorbance. So these are just samples. And we hope that our samples is accurate enough to estimate the true relationship between Y and X, the true relationship between absorbance and concentration. Since we use sample, we have to modify a little bit the expression on the constants. So we use B0 to estimate beta 0 and B1 to estimate beta 1. You see the change here? So instead of using beta 0, where beta 0 is the true intercept, beta 1, the true gradient, and we use B0 as an estimate of beta 1, B0 as an estimate of beta 0, and B1 as an estimate of beta 1. So we get this from the sample, that we make up from standard solution with series of concentration. This one is Y value with a head. There is the term used is Y head because it has a head on top of Y. Is the estimated value, the value of Y exactly on this line. Value of Y exactly on the line. These are Y head. Whereas the observed value of Y is from the experimental value. This is the observed value of Y. And Y hat are the values of Y exactly on the line. So that's why there's no error term here. If we want to include the error term, it should be Y equal to B0 plus B1 X1 plus some error term. So if you want to include, if you want to use Y, we should include some error term because there are points which are not exactly on the line. When we use this, meaning that Y hat has value exactly on the line. In order to define the equation, we have to estimate these two parameters, B0 and B1. And the method used to obtain B0 and B1 is called the least square method. It's called the least square method. Okay, let's say that we did this experiment with concentration of sample standard solution ranging from 10 to 50 ppm. And we measure the absorbance value of this solution. And then we want to plot the straight line curve. Let me ask you a question. How do you find this line? Which is good. Any particular software that you use to get the line? So, anything that you used before Excel? You were born with Excel. Graph paper. How do you use the graph paper to get the line? It's mostly trial and error. We adjust the line. How do we adjust the line? Based on distance. So before Excel, once upon a time before Excel, we define the line by adjusting our ruler to satisfy all the points. Remember, so that the line will be as close as possible to all the point. We don't want to have a curve like this, where it's very far from here, although it's very near with this point, but very far from here, or like this, which is also wrong, because this one will be very far. So we try to get the best line that satisfies all the points. We try to get the best line which satisfies all the line. And this is called the least square method. How do we do that by using computer method? If we look at the line again, let's have some points here. We try to find a line which satisfies all the observed value, and there must be an error for each point. This error, error. In the least square method, we try to minimize the error. We try to minimize the error. The term least square meaning that the least square of error. What is the error? Let's say this is yi, and remember this is y hat. The point exactly on the line is called y hat. So this is yi, the observed value, and this y hat. The error is yi minus y hat. And we square the term. We square the error term because otherwise the total error will be 0, right? We have some positive and negative error. So if we just sum up all the error without squaring the error term, we'll get value of 0. So that's why we have to square the error. And let's call this Q. And we sum up for all points n, where n is number of points in the data. Let's clear this a little bit. The total error Q is the sum of yi minus y hat squared. And we sum up all the error term for all points in the sample, in the data set. This equation here. So the objective is to minimize the error term Q, to make Q as small as possible. To make Q as small as possible. So if you can see, if we find the right line, the Q value will be as small as possible. The Q value will be small as possible. So that's why it's called the least square method. This one here, yi minus y hat. We sum up the error term, Q, and the objective is to find a line. Basically, the line is defined by two parameters, B0 and B1, right? The line is defined by B0 and B1. So once we define the line, so we get value of B0 and B1, and we can save B0 and B1 and use those values to predict the concentration of unknown sample. Any question up to now? How do we derive B0 and B1? That's probably beyond discuss. This is probably best discussed in statistic course. How do we derive B0 and B1? Let's say we have B0 and B1 here, y hat equal to B0 plus B1. So this is what how we can measure B0 and B1. This is the equation. I don't want to go through the derivatization of these two values. We just use it. And once we got B0 and B1, we can save the two values and use it for prediction purposes. We can simplify the equation to be like this. We sum up xi value, sum up the y, sum up the x squared, sum up the x times y, and you got B1 from this equation and D from this. Let's take a look at an example. Let's say we have series of solution with 10, 20, 30, 40, and 50 ppm. And we measure the absorbance value of the standard solution. And let's say these are the absorbance value for 10, 20, 30, 40, and 50 ppm. Let's take a look at the sample. So in this particular example, we have 5 observations for solution ranging from 10 to 50 ppm. And we measure the absorbance value. And we can calculate the sum of x here, sum of y, sum of xy, and sum of x squared, right? We total up all this, and we get a B1 of 0.00581 and B0 of 0.035. And this is the equation. This is the simplest equation that we can get using a regression equation. Yeah? And I don't know, maybe tomorrow you should bring your laptop so that we can do the exercise using Excel. Maybe either tomorrow or next week. And this is done manually by using simple calculation. Okay, so that is how we derive the equation relating the ppm, the concentration, and absorbance values of the standard solution. In any statistical result, there must be a measure of how good is the of our result. How good is our result? For example, we can use standard deviation to measure the precision of our data. So in straight line relationship like this, we can use the term, the statistic called standard error to measure how good is our line. To measure how good is our line. And the equation used to calculate S is this one. S equal to y minus y hat squared divided by n minus 2. And if you look at the equation closely, there's a very similar form with the equation for standard deviation. So if you had one single measurement, the standard deviation for this is xi minus x bar n minus 1 square right? Am I right? This is the equation for standard deviation. This is for single measurement. Let's say if we make measurement in the lab, and we can let's say we have 5 replicate measurement, and the precision of our measurement is measured using standard deviation. You see how close is this to the standard error? So the term can be used to indicate how precise is your line. How close are the points to the line? So if we had a small standard error, meaning that all the points are very close to the line. Whereas if we had a large standard error value, meaning that the points are spread, not close enough to the regression line.